In this video, I want to develop the two limit definitions for the derivative that we're going to use in calculus. First of all, we want to be reminded that what the derivative is, and that is that the derivative is the slope of the tangent line. All right, so what I have drawn here is just the curve y equals f of x. And I'm going to identify this specific point, 1.5 f of 1.5. Now, since the derivative is the slope of the tangent line, what I have here is the line tangent to f of x when x is 1.5. Next, I'm going to take some other point on the line, just x f of x, and I'm going to draw the secant line to that. Now, obviously, this isn't the tangent line, but it is the secant line, and I do have 2 points. I mean, I've got 1.5 f of 1.5, and then this other point, x f of x. So I can find the slope between them. Remember that slope is change in y over the change in x, so our change in y is going to be f of x minus f of 1.5. And our change in x's are x minus 1.5. So we can find the slope of the secant line. Now, the secant line is really just an estimate of the tangent line. Looking at this picture, it's a horrible estimate, almost a complete opposite of what the tangent line is. But as I move the point around, I can come up with a better estimate of where the tangent line is. In fact, if I move it all the way over so that my secant point lands right on top of my tangent point, well, then we do have the tangent line. Because even as we get very, very close to that 1.5, we can still calculate that slope because I have 2 distinct points. As soon as we move that point all the way over until it's right on top, then we don't have a way to calculate it anymore. Or do we? Because we do have this idea of the limit. And when we think about this picture and what's happening, as I'm moving this point closer and closer to my point of tangency, what I'm doing is taking this x-coordinate and letting it get closer and closer to that 1.5. So we can use the limit alongside our definition of what we've got for the slope to help us calculate the derivative. To do that, I'm going to start with my definition of slope, which we just said is f of x minus f of 1.5 over x minus 1.5. And our whole idea was to let that x get closer and closer to that 1.5 until it's right on top of it. So that means that our derivative, which we'll call f prime of x, is going to be the limit of this function, f of x minus f of 1.5 over x minus 1.5. That's just the slope of our secant line. But we're going to let the x that's in that second point, move closer and closer to 1.5, the x-coordinate of our point of tangency. Once that happens, we will have not the derivative at x, it's actually the derivative specifically at 1.5. So what we just found is called the numerical derivative, and that's the actual number value of the slope of the tangent line at a given point. The definition is for any real number a, the derivative when x is equal to a is going to be called f prime of a, or the derivative of f at a. And that'll be the limit as x approaches a of f of x minus f of a over x minus a. To find the other limit definition of the derivative, we have to shift our attention to the other point. And let's keep that one fixed. The idea is still the same, that I can't find the slope of a line when I only got one point on it. So I'm going to look at another point and check out the secant line and pay attention to the slope of that secant line and trying to get it to look like the tangent line. To do that, I'm going to recognize that that point is h units away from my first point. That first point is at some x value, and then its y coordinate is f of x. But the second point is h units away from that. So that means its x coordinate is whatever x was plus h more, and its y coordinate f of x plus h. Now, as we move that point closer to our point of tangency, we get a better and better approximation of what the tangent line is. But pay attention what happens to the length of h down here. As we're trying to move our secant point closer to our point of tangency, that distance is really getting smaller and smaller until we are right on top of that point of tangency, and the distance between those 2 points then is nothing. So let's start back when we have our point on the secant line way over here, and think about what would the slope look like. And once again, our slope is going to be that change in y over the change in x. So going from that secant point, its y coordinate, f of x plus h, back to our point of tangency, f of x, then we'll be over x plus h minus x. Of course, the x's in the denominator cancel each other out, and we have this expression, f of x plus h minus f of x all over h. And that will give us the slope of our red secant line. Of course, when we wanted to find that derivative, the slope of the tangent line, we're going to start with our slope of the secant line, f of x plus h minus f of x all over h. And the whole point was to get that point that's on the secant line to come all the way over to the point that's on our point of tangency, which means that h has to get smaller and smaller. So we're going to take a look at this expression, but we're going to let h get smaller and smaller until that distance between those 2 points is 0. So the functional derivative says for a given function f of x, the derivative at every x in its domain is given by the function f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. The big difference here is that the functional derivative is a function. It should look like an equation. When we're talking about the numerical derivative, that's a number at one specific point. The functional derivative gives us the derivative for any value of x on the function. That makes it a little bit more versatile when we're trying to define some rules or look for shortcuts or just find multiple tangent lines across a given function.